So here in this experiment we are going to find out heat transfer through a pin fins. So let us first know what is a pin fins. So these are the extra projection surface over the cylinder heads to transfer the heat to the atmosphere. So here in this experiment we are going to determine the effectiveness and efficiency of the pin fin under natural convection and forced convection heat transfer. Fins are extended surface made up of highly conductive materials such as aluminium, brass, etc. are used to enhance the heat transfer from the surface. In convective heat transfer, the heat transfer rate depends upon film heat transfer coefficient, that is what we represent with a small h, and surface area with a capital A, surface and ambient temperature. For certain applications, the surface and ambient temperature are fixed. The heat transfer rate can be increased by increasing the convective heat transfer coefficient or by the increase in the flow surface area. The flow surface area can be increased by attaching extended surface called fins to the base surface. Fin surface are manufactured by extruding, welding or wrapping a thin metal sheet on the surface. Fins are various shapes such as circular, rectangular and triangular. Fins are used in various applications such as radiator, motorcycle engines, refrigerator and cooling of electronic equipments. So let us now see the experimental setups. What are the things we can see here? The setup consists of rectangular duct. So this is what we see, the rectangular duct. One is connected to the section side of the blower and another end is open to the air. So here you can see that one part is been connected to the section side, another part you can see that is being exposed to the atmosphere. So one end of the fin is fixed to the duct and heater is being provided. Blower is provided to achieve forced convection by blowing the air over the surface of the fin. 5 thermocouples are fixed on the fin to measure the surface temperature of fin. So here you can see the thermocouples have been placed to find out the temperature on the surface of the fin. In addition, one thermocouple is fitted outside the setup to measure the ambient air temperature. So here in this setup, here we could not able to see, but they have been placed in one thermocouple outside the atmospheric surface so that you can find out the temperature over the ambient temperature. Airflow rate is measured through orifice meter and verify the flow rate by manometer. So we have been having here the manometer readings where you can find out the flow of the water or flow of the air. So now let us find out how this experiment is being conducted. First we are going to switch on the system. This is the thing we are going to switch on. Then afterwards we are going to switch on this heater. Then afterwards we are going to adjust the flow of heat for the heater to maintain a constant temperature. We need to wait for a few minutes to have a steady state of temperature. So it should not change within a time. Note down the temperature from T1 to T5 and ambient temperature, that is T6. Repeat then experiment by varying the heat input. So for next reading you need to change this regulator flow. So what is the amount of heat required? So for successive heat transfer we are going to find out the readings. So after that one we are going to calculate the efficiency, effectiveness and temperature distribution on the fin. Now let us look on for the observation. What are the values already we have been having? We know the diameter of the fin, that is d is equal to 12.5 mm, and length of the pin fin, that is L, it is denoted by capital L, that is 150 mm. Then duct size, that is 140 mm into 100 mm. So diameter of the orifice, that is been 12.5 mm, and diameter of the pipe, that is 50 mm, and coefficient of discharge is 0.62. and fin material we have been using here the aluminium. The thermal conductivity of aluminium and the brass we have been taking. So that aluminium you need to find out from the data handbook, and here for the brass it is been given 204.2 watts per min Kelvin, and perimeter of the pin fin we need to find out pi d, that you have to keep it in mm. So now let us look for the tabular columns. What are the readings you need to take? So when you are going to keep the flow of current constant for the heater, you can find out the value of the voltage and value of the ammeter. From this you can find out what is the input given in the form of watts. Then you have been having a room temperature to find out the thermocouple, which has been measured as T1, and the surface temperature to measure we have been having T2, T3, T4 and T5. So after this we are going to find out the heat convective. Then afterwards you are going to find out the effectiveness and the efficiency of the pin fin. So to find out those things, we will now go through how the calculations need to be carried out. So here we need to find out the cross section area of the pin fin. So here the area we need to find out, you know the value of the D, that is in a diameter of the pin fin which is been given. So if you substitute the value of the D, you could able to get the area of the pin fin. Then perimeter of the pin fin, so you know the value of the D, then you can find out the perimeter. Then surface temperature of average we are going to take, that is T2, T3, T4 and T5. So you are going to get a surface temperature average. Then heat transfer coefficient calculation. So theoretical correlation we are going to find out. We are going to find out the film temperature. Here the surface temperature average what you have been taken, and the T1, that is an ambient temperature, that is a temperature at the air. So you could find out the film temperature. Then volumetric efficiency, that 1 by film temperature plus 273 Kelvin, that we are going to find out. Now note down the properties for A for the film temperature. For this film temperature, from the data handbook we are going to find out what is a kinematic viscosity, density, thermal conductivity, Prudhon's number from heat and mass transfer data handbook. From this substitute all those values in this number, you could able to find out the Grashof number. Then afterwards, if you know the Grashof number and Prudhon's number, all those from the heat and mass transfer data handbook, we are going to substitute this one in the Nusselt number. For a constant heat flux and all the values you have been getting from the data handbook. From the Nusselt number, heat transfer coefficient can be calculated very easily. You know the value of the D and you know the value of the K, that is in a thermal conductivity. You know the Nusselt number. From this you could able to find out the heat transfer coefficient theoretically. Okay, so now the pin performance parameter we need to go through. Once you know the value of the heat conductive, so you have been having the equation for effectiveness of the fin. You know the value of the K, you know the value of the P, that is in a perimeter, you know the value of the H, and you know the value of the A. Then substitute the value of M and L for this time. For the M we have been having this one H P by K. So H, you know the convective heat transfer, P is the perimeter, K is the thermal conductivity, and A is the area we could able to find out. So substitute the values M here, and here the length of the duct we know it. So substitute those values, you will get the effectiveness of the fin. Then efficiency of the pin fin can be calculated very easily. You know from this equation we are going to calculate the value of M. Then substitute here, you will be getting the efficiency of the pin fin. So till now what we discussed, that is been related to a free convection. Now we will go for the forced convection. In this forced convection, the procedure is the same thing, but here you are going to switch on the blower. Here also the same thing, we are going to find out the cross section area of the pin fin and the perimeter of the pin fin you are going to find out. Then surface temperature you are going to find out. So all these values D already it is been given, and the temperature we are going to find out from this tabular column that we have been taking from surface temperature from the thermocouple. Here the film temperature is been calculated from the surface temperature, and the ambient temperature we are going to take average. So from this we are going to find out now what is the value we have been got it. From that one we are going to find out from the data handbook the different properties of air, that is kinematic viscosity, dynamic viscosity, density and thermal conductivity, and Prudhon's number from the data handbook. So then we are going to substitute those values here in the Q, that is equal to CD into area of the orifice, the root of 2G HA. The HA is the value here it is been given. Okay, so you will be getting the value of the Q. Then here the value of the Q you are going to find out from this equation. So from this equation, all this you are going to put forth in the Nusselt number, and before that one we need to find out the Reynolds number. So then afterwards you will get to know the Nusselt number. Then you are going to substitute the heat transfer coefficient. Then you are going to get the value of heat transfer coefficient. Then same thing you are going to substitute here the effectiveness of the pin fin and effectiveness of the fin. By substituting that heat transfer coefficient, you could able to get those values. So here whatever the value you have been got, it is in a forced convection. The difference is that in the free convection you are not going to on the blower. So in the forced convection you are going to on the blower. For that, what is the readings you have been got it, so you are going to take. So you can see the difference. For the free convection the equation are different, and forced convection the equations are been different. This we have been got it from the data handbook.